So, now next we come to the various kinds of actuators, how to actuate the valve. So, we have various kinds of actuators. We have electromagnetic actuator or solenoid actuators, we have pneumatic actuators, we have sometimes for large valves we have hydraulic actuators, right. So, we can also typically we can also have mechanical actuators also, manual actuators. So, in this case we will typically look at two actuators, one is a solenoid actuator and the other is a pneumatic actuator. So, solenoid actuators have higher speeds, they are lower ratings, but higher speeds because as we will see that the force on the actuator can be quickly controlled because it is controlled by current. So, current can be driven pretty fast. So, therefore, forces can be created, very fast varying forces can be created, and therefore, the valve actuation becomes fast. On the other hand, for pneumatic actuators, the force is created by by bringing pressurized air on to work on a surface or a diaphragm. So, since there is some volume involved, so there is certain amount of time required for that air to come and fill the chamber and then create the pressure on the diaphragm. So, pneumatic actuators are always generally slower than solenoid actuators. So, we have higher speed, lower size because pneumatic actuators can be of quite high size, I mean of larger size, because just by increasing the diaphragm sometimes we can create a lot of pressure. For even higher ratings we can use hydraulics. So, solenoid actuators are generally of lower size and often they are used, as we will see, they are often used in pilot stages of electrohydraulic valves. So, you have a big controlled valve and you want to move the valve. So, see that big electrohydraulic valve actually maybe controls the flow. Now, to move the valve also you need to create you need to move the valve. So, you have a valve, oops, okay, this is the installed characteristic. Page up. Just a moment. Yeah. Yeah. So, we are talking about solenoid actuators, that they can be used in pilot stages. I don't know why this is creating a problem. Okay. So, right. So, what I was saying is that the electrohydraulic valve pilot stages, the solenoid valves are used, and this is a particular construction of the solenoid valve. So, you see that this is the valve, this is the plug, and this is the closed position shown. So, this is inlet and it's flowing through this and going to this is the flow of fluid. There is a spring loading. Now, this is here the stem is actually connected to a magnetic core which is called the plunger, right, and here you have a high current carrying, high force creating coil. So, this is the coil assembly, solenoid coil housing. Okay. Shedding coil is used to guide the flux through the core, so that the proper force is created, and flux, actually the force is created by the flux. So, one has to guide the flux so that an upward force is created. So, and this is the movable core, this is the tube through which the core moves, these are the connections. So, what happens is that when the coil is de-energized, then the spring will push and keep the valve closed, right. On the other hand, when this will you see that if this is energized, then the flux is flowing like this as shown and it is pulling the plunger up. So, when the pulling the plunger up, then the spring is compressed and this opening is open and the fluid flows. So, this is the way a solenoid actuator will work. This is, on the other hand, this is a particular pneumatic actuator. So, again same thing, again you have a plug and you have these ports. So, what happens is that here by spring force, this is a particular valve where you can close the valve by applying air. In the normal position it will stay open. So, there are various kinds of valves, as we shall see, that if you apply energy or force they will close, or if you apply energy or force they will be open, they will open. So, in the previous case for opening the valve we needed to apply current. In this case for closing the valve we need to apply air force. So, the air will enter here, this is the diaphragm on which it will create a pressure. So, the pressure multiplied by the area of the diaphragm will give the force, and this force is going to push it down and close it, right. So, this is the operation, basic operation of a pneumatic valve. So, as we shall see that if you see the characteristics of this valve, then obviously there are, as we said, that there are forces acting on the plug, because when the fluid is flowing out through the orifice it is actually pushing the plug up or down depending on the flow profile. So, there are forces acting on the plug. So, what happens is that because of this the plug, the valve stem position percent and the diaphragm pressure, see there are two things. Firstly, diaphragm pressure to stem position. So, how much diaphragm pressure is required to create what stem position, and then stem position to flow. Stem position to flow characteristic is essentially guided by the construction of the valve and the applied delta P. On the other hand, the diaphragm pressure applied to stem position is essentially affected by how much force is actually acting on the stem. So, when you have high plug forces, then this stem position to diaphragm pressure characteristic gets shifted, right. So, by applying and what is controlled? What is controlled from the controller is actually the diaphragm pressure. Actually there is a controlled air supply, pneumatic source. So, what amount of pressure will be applied on the flow control valve diaphragm, that is what is controlled. So, if the stem position diaphragm pressure, so in open loop control we will there is some gain calculated. So, people will think that now okay, so this is the flow, so now I know the flow characteristics, so therefore this much of stem position must be realized. So, for realizing this much of stem position I have to apply this much of diaphragm pressure. So, that much of output will come from the controller. This is the way the valve is going to be controlled. But it so happens that this stem position to diaphragm pressure characteristic will change depending on whether there is plug force or not. So, depending on the plug force we may or may not be able to, and the plug force depends on so many things. The plug force depends on the current value of pressure in the pipe. So, we need to make, it is necessary to make valves invariant to such variations of force. So, it is for such purposes that we often use what is known as a valve positioner. So, valve positioner is actually itself a control system. So, what it does is the following. So, you see that in this case this is the valve, right. This is the valve stem, again there is a spring, and this is the diaphragm on which the pressure is being applied, right. So, the diaphragm is coming from, the air is coming from here, and it is through this valve that the pressure, the position of this spool that the pressure here is being controlled. right. So, how it is being controlled? So, we are applying a 3 to 15 PSIG input signal, which is a low power input signal, that is being applied here in this chamber. So, that creates a force on this. Once it creates a force on this spool will move downward. So, when it moves downward, the air supply, which is a high pressure air, will flow through this and will come here. So, depending on the opening, there will be a kind of pressure drop, and the final pressure will be realized here. Now, as this pressure increases, this thing now starts moving downward and the valve opens. On the other hand, because of this mechanism, when this comes downward, there is a force applied upward. So, you see it's a force balance principle. So, finally, whatever pressure is being applied here, that must be balanced. That will be balanced by this. That will be balanced by the spring force as well as this force. So, therefore, since this is an applied pressure and the spring force depends on the displacement. So, therefore, for a given pressure here, the valve will, as long as this force is not balanced, say when this force is higher, then it will start opening and this pressure will keep increasing. As it is keeping increasing, this is trying to come down, and therefore, this is going to go up, increasing the spring pressure. So, the spring pressure will actually balance this force when a particular displacement of this spring takes place, and by the mechanism, a particular displacement of this spring implies a particular displacement of this stem. So, therefore, when you apply a particular pressure here, a particular displacement of the stem is achieved, irrespective of what are the forces here. So, till this displacement is achieved, this will start moving, and obviously this should have enough power to overcome this force. So, but if you have created enough power, then just enough force will be created here, so that the final displacement will actually balance this pressure. So, the final displacement is always invariant, irrespective of whatever is the force on this stem. So, in this way you achieve a particular stem position to control input signal. It does not depend on the plug force, right, because by closed loop control. So, such a thing is called a valve positioner. There are various other mechanisms. There is just one mechanism which we have shown. There are various other flapper nozzles based mechanisms, etc. So, now we come to take a look at some valve characteristics. For example, there are certain characteristics of the stem position movement, especially dynamic characteristics, right. So, if you give a small value of command, the stem position will be this much. If you give a large command, it will be this much, but you see there is a certain restriction on the rate at which the stem can travel, right. So, therefore, you cannot give very large and at the same time very high frequency commands. If you give them, then that input command will not be realized in terms of stem position, and you will get responses like this. So, for example, if you give a large and then high frequency sinusoid, then the stem position will not be able to follow it, but rather it will go up like this. So, there will be a distortion, So, these things have to be kept in mind when one is designing a process control loop with a valve, right, that they have these rate limits. Any actuator, most of the electromechanical actuators actually have a rate limit. Similarly, there may be hysteresis in the stem position due to various factors. So, when you are increasing the pressure, the stem position may actually follow this curve, and when you are decreasing the pressure, it may not follow exactly the same curve. Now, such dead bands, as we know from standard nonlinear control systems, often give rise to oscillations. So, these process control loops, flow loops, if you give an alternating command, then the process control loop may actually oscillate. So, these are called limit cycles in the closed loop. Similarly, these are sometimes there is a very important quantity for a valve called a rangeability. So, rangeability means that what is the maximum to minimum flow ratio. So, the maximum flow to the minimum controllable flow is it is said. So, valves can have sometimes valve manufacturers claim that they have 10:1, 15:1, 13:1, 30:1 kind of rangeabilities. So, sometimes in some applications it may happen that you need a very high rangeability, that is you can sometimes need very small flows, sometimes you need very high flows. So, in such applications you sometimes have to have valve sequencing, that is you actually have more than one valve, and in one part of the operating region you operate one valve, and in another part of the operating region you operate another valve. But you have to ensure certain things like transitions such that suddenly the when you move from one valve to another valve, the process control loop characteristics do not change. So, one of these is by split range control, which we have also seen in the case of our process control module. So, you have two valves and they are fed through an amplifier and a bias, right. So, these biases are made different, and in certain parts of the region the actually the control signal comes to this valve. So, this valve will operate, then after some time when this valve input will actually saturate, then this valve will operate no longer, and then this valve will start operating. So, so the overall range of operation is split using this gain and bias mechanisms, and in different parts of the operating region different valves are employed. Similarly, sometimes you can have, there may be another scheme. This is another valve sequencing scheme where you have a pressure sensor. So, this pressure, this is actually the controller output which is going to the valve actuator. So, when the controller output, so here the switching, which is by these three-way valves, is actually done based on how much controller output is being exerted to these valves, and depending on them one of the valves will be operating, either this will be operating or this will be shut off or this will be vented and this will be operating. So, and it turns out that for such sequencing, when you will, for example, typically the gain of large valves will be actually larger than the gain of small valves. So, one has to ensure that when you are switching from the small valve to the large valve, the gain is not, the gains do not suddenly change, because that is going to change the overall gain of the process control loop and may bring in things like instability problems, instability or saturation problems. So, for doing that is why it is, for such kind of sequencings, equal percentage valves are actually better suited, because as we know from the equal percentage characteristics, the equal percentage characteristic is like this, right, same position to flow. So, you see that for the small valve, when you are just before closing the small valve, the actually small valve actually has a very high gain. So, when you are switching on from this gain to the gain of the large valve, so the large valve actually has a high value of gain, but it is operating in its low gain region. So, we are transforming from the high gain region of the small valve characteristic to the low gain region of the large valve characteristic. So, therefore, the gain switching, suddenly when you switch from the small valve to the large valve, the overall process loop gain does not suddenly change. So, this is one reason why equal percentage valves are better suited for valve sequencing rather than linear valves. Often, as we have seen that, as we know, I mean this shows that often valves are actually put in the closed loop. So, it is actually a part of the flow control loop generally, and if you have a that is, rather than suppose you have a temperature loop. So, in the temperature loop output, controller output, rather than giving directly to the valve, which has nonlinearities, which has dead bands, which has hysteresis as we have seen, it is better to set up a flow control loop, which is a slave loop, in the sense that the temperature control loop is actually the master control loop. So, the temperature controller output will give a flow set point, as we have seen in the case of cascade. So, what will happen is that, so if you set up, so this is the one coming from the master, say, temperature control loop. Then if we set up, this is the flow controller, this is the flow transmitter. So, if you set up, then even if the valve is nonlinear, the characteristic of this loop, that is between this point and this point, are much more linear. Let us say it may not be absolutely linear in a mathematical sense, but there will be much more linear, and that makes it much easier to actually design and ensure that the characteristic of the temperature control loop remains uniformly good over the whole region of operation. So, sometimes many times we set up this kind of loops. Sometimes valve characteristics can be very cleverly used to match the system characteristics. So, for example, take the case of a liquid to liquid heat exchanger. So, what happens is that now this is the input, which is the cooling flow, and what is the output? The output is the outgoing temperature of the liquid which is being heated, let us say. So, when there is a slow flow rate, that is when this flow rate is low, then obviously this liquid stays within the tube for a longer time, and therefore, for both the gain between this point to this point, there is a temperature for a given rate of flow of the heating liquid, the increase in temperature between the inlet and the outlet will be higher. Not only that, this will be also the delay between, if you make a step here, then this will go up, but the delay between this step and this step will also be higher, because of the fact that the liquid is travelling slowly. So, but on the other hand, when you are so you see that this is a situation where you have high gain and you have a high delay. So, you need to keep, as we know, that the controller gain needs to be kept low in this region. On the other hand, if this flow is increased, if this flow rate is increased, then the gain will fall and the delay will also fall. So, now is the case when you can have for better improved transient performance, you can have a higher controller gain, but it is not automatically easy to actually change controllers. So, for this application, if one uses an equal percentage valve, then as we know that the valve gain goes up as the flow rate goes up. So, automatically the loop gain increases as the flow rate increases. So, the overall process loop transient characteristic is maintained uniform simply by the valve characteristic, simply by the choice of the valve, right. So, this is what I am saying. Similarly, at the an opposite situation can occur if you have an orifice meter. So, in an orifice meter, as the flow rate increases, the sensor gain also increases. So, again the loop gain increases. So, in such a case, one has to have the overall gain reducing, right. So, one can use a linear valve for this. Lastly, valves are, one has to have a view towards what will happen if the actuation fails, because sometimes these flows can actually cause explosions, etc. So, valves are constructed in various configurations which are shown here. For example, fail open or air to close. So, if this air supply somehow fails, then this valve will fail, and it will fail in an open situation. So, if the air supply is not there, then the valve will remain open. Similarly, there are air to open valves where if the air supply fails, then the valve will close. So, one has to choose a particular actuation configuration to avert industrial accidents under various kinds of failures. So, that brings us to the end of this lecture. So, as a matter of review, we have typically seen globe valve, ball and butterfly valves. We have seen various kinds of valve flow characteristics, both static and dynamic, and we have seen how valves are actuated and controlled. There is one aspect which is treated in books which is called valve sizing, that is for a given application determining the size of the valve. We are not talking about that, because this is essentially a process design exercise and does not concern automation and control. So, to end, points to ponder: first is sketch the cross section of a globe valve and indicate 4 of its major parts. You should be able to do that. What is the difference between installed and inherent characteristics? This is extremely important, and why this occurs. What is the main advantage of a valve positioner? Why one puts it? And finally, mention one advantage of a solenoid actuator over a pneumatic actuator and one advantage of a pneumatic actuator over a solenoid actuator. So, that brings us to the end of the lecture. Thank you very much.